Wow, that's loud. Today's speaker is Nienhuis. Did I say that correctly, Nienhuis? Yes. I work for a Dutch company, but they don't make us take Dutch lessons yet. Jaap is a postdoctoral fellow in Earth and Environmental Sciences at Tulane, working with Torbjorn Tornquist. And I noticed your collaborators are cut off there a little bit, so we might have to adjust this. We tried. Oh, okay. So we're stuck with the AV system here at the Holiday Inn. Jaap attained his BS and MS in civil engineering from the University of Twente in the Netherlands, and his PhD in marine geology from MIT and the Woods Hole Oceanographic Institute. His experience includes morphologic modeling of coastal sedimentary environments, which is what he'll be talking to us about today, predicting delta morphology on a global scale. So, yeah.
All right. Well, thank you. Can everyone hear me okay? Yes. All right. Thank you. This won't interfere with mine. Yeah. All right. Thanks for the invitation. This is my first time here, and it's great to see so many of you. Let me also drag this box. Try to interfere. No, oh well. This might be the best I can do. Yes. So as Alex said, I'll be talking about predicting delta morphology on a global scale. For example, predicting something about the shape of the Mississippi Delta, but then not just for the Mississippi, but for all deltas globally at the same time. And in particular, I've done this with a lot of people, but in particular, I'd like to acknowledge my thesis supervisor, Andrew Ashton from Woods Hole, and my current postdoc advisor, Tor Tornquist at Tulane. So before I go into predicting deltaic morphology, what exactly are river deltas? And I'm aware that most of you are geologists, but just a very brief introduction. River deltas are environments where fluvial sediments have accumulated in lakes or in oceans because, of course, the velocity of the river slows down as it enters a standing body of water. And over thousands of years, millions of years, all this sediment builds up and attains these very interesting shapes that vary tremendously between different delta systems. And because they deposit in a standing body of water, they usually are very flat environments, basically at sea level. And river deltas are literally everywhere along the coast. This is a map I made collecting where different deltas might be. And you see that they're everywhere. And the definition of what exactly a river delta is varies from person to person. But in this map, there are about 14,000 of them globally. And river deltas are, in part because of that, very important. They're home to about 500 million people. And that is because they're associated with very high productivity and biodiversity. But unfortunately, they're also one of the most rapidly changing environments on the globe. And that is in part because they're so low-lying, so things like sea level rise and subsidence can induce big morphologic changes, but also other things like changes in storm conditions and hurricanes. And because they're formed by fluvial sediment, if you change things upstream of river deltas like river dams or changing land use, that will also then affect the shape of this delta. So the aim of my talk today is a very simple question. Given that deltas are so important, can we then predict deltaic change globally for all deltas in a standardized and robust manner? Before we get into predicting deltaic change, of course, you first have to know what controls delta shape to begin with. So this is an example delta here on the coast of Mexico. And before you can know how that delta is going to change, you have to know why this delta has attained this shape in the first place. The second very important part is how deltas will be affected. So things like climate change, humans, or natural variability of these systems. And lastly, if you combine those two questions, then you can ask yourself, well, how will deltas change in the future? So what controls delta shape? I'd like to phrase the question a bit differently, and that is how to connect boundary conditions to delta shape. If we're interested in predicting deltas globally, so all deltas at the same time, you need to know how boundary conditions, so things like water discharge, sediment load, and grain size, or waves and tides and sea level, so external controls on deltas, how they then determine the internal geometry of the shape of this system. So all of these factors here are not influenced by the delta itself, but they are controls, they're external controls on the shape that results. And if you have any questions, please just raise your hand or clarifications, and I can address them. And this is really important, for one, because we want to predict changes to these deltas, but also this is really important for paleo-delta reconstruction. So for example, if you find an outcrop with a collection of channel bodies, how does this compare to the broad delta morphology that existed at that time? And if you know something about that broad delta morphology, can you then say something about things like wave or tides or sea level? So to make that connection quantitatively, you need to know how these external controls affect delta shape. And also this question what controls delta shape is really important for incorporating deltas into global models. So people are now starting to think about the Earth system as one big model where they can include things like land cover, biodiversity, soils, and climate to predict what Earth will look like 100 years from now. And to do that, you need to have some quantitative understanding of how all these things then affect river deltas. Of course, I'm not the first to consider delta shape. Some of the key papers that have addressed this topic were from Galloway and Wright and Coleman and Orton and Redding already quite some time ago. And in particular, I'd like to note this Galloway triangle that probably most of you are familiar with. What Galloway did in his paper in 1975 was say, well, we can address some of the variability of river deltas by looking at three different things. So he said one thing, if deltas are dominated by waves, they'll attain this very smooth coastline shape here. On the other hand, if deltas are dominated by tides, you get these alluvial channels carved out by tidal motion. And if both those things don't really occur, are not really important for the delta, then the river itself will dominate its morphology. And this is a very good description of the variability of deltas we see globally, but there is one very important problem, and that there is no way to quantify whether or not one of these shapes will occur. So for his paper, he said, well, things like discharge is probably important to make something river dominated, or something like tidal energy is probably important to make something tide dominated, but what kind of delta will there be for something that has 100 watts per meter of tides or 20 cubic meters per second of river discharge? We don't, or 200 micron of sand. We have no connection between all of these factors and the shape of the delta that results of those combinations. So that's where I come in. And I asked myself a very simple question: what exactly, how many tides do you need, or how many waves do you need before something is wave or tide dominated? So I try to, in order to predict all deltas globally, I want to quantify this Galloway triangle and say for a specific delta where in this triangle does it plot. So let's start with wave-dominated deltas. As I said before, wave-dominated deltas appear when you have very strong waves, and they tend to smooth out the coastlines. And a lot of people have considered this before, and what they found was that if you have some fluvial sediment coming from the river, if you have very strong waves, they tend to remove that sediment from the river mouth along shore by what we call a littoral sediment flux. And that process of redistributing fluvial sediment results in that cuspate, very smooth coastline shape. So what is this littoral sediment flux or alongshore sediment transport? Well, that occurs if waves approach at an angle, and when waves approach at an angle, they tend to refract towards the coastline. And if they do that and break at the same time, they set up an alongshore sediment transport. So if waves approach straight on and don't refract, there is no alongshore sediment transport. But when waves approach the coast at 45 degrees, so here and there, you get a maximum amount of sediment that particular wave can move along the coast. So can we use this understanding to say something about these deltas? Well, in one very simple condition, we'll have this straight coastline again and one wave that approach from straight on. In that case, of course, there is no refraction of that particular wave, so you don't have any alongshore sediment transport. You're here at the origin of this function. In another example, let's say we have a river that puts in some amount of fluvial sediment. That sediment tends to pile up around the river mouth, and because of that angle that sediment makes with respect to these incoming waves, you now have a wave that approaches the angle, that approaches the coastline at an angle. And that angle then creates a alongshore sediment transport, so that is the origin of this smooth coastline shape. So can we use this to say something predictively about delta shape? Well, what I've done is I've adjusted this formula to say something not for one particular wave, but for a whole distribution of where waves might come from, and a whole seasonal cycle and all of that. And what you can then do is look at not just wave approach angle, but shoreline orientation, so how pointy or how deflected this coastline is. Now let's say all this fluvial sediment that came from the river, half of that goes to the left and half of that goes to the right. What you then end up with in a steady state is that half of that transport that went to the right and half of that transport that went to the left attains some equilibrium with respect to the wave, such that you have an equilibrium pointiness of your river delta. This also gives us a prediction of the most wave dominated a delta can ever be, is that if you don't have any fluvial sediment coming from the river, there is no angle that this delta will be able to set up. So then you'll have a very straight coastline. So this is, in our Galloway triangle, this is that far corner there, where you don't have any fluvial sediment, or you have such strong waves that they very quickly redistribute sediment along the coast. Of course, if you have a lot more fluvial sediment, then you can be so pointy that waves approach this maximum efficiency where they're at about a 45-degree angle with respect to the coast. And in that case, you have two flanks of your delta that are oriented 45 degrees. And so this is right here at the border, because you cannot be any more wave dominated than this one. But of course, what if you put in a lot more fluvial sediment? Well, then you quickly reach into a scenario where you don't have any coastline orientation that is stable for this condition. So in that case, you develop a river-dominated delta. You put in so much fluvial sediment that there is no wave approach angle or shoreline orientation where this condition is stable. So in that case, your morphology will start to bifurcate and be dictated with things that the river wants to do. The important part of this message here is that we can make a ratio we call R, where we divide the fluvial sediment flux by the amount that waves move away from the river mouth, and this gives us a non-dimensional ratio of delta morphology in the case of wave dominance. So for R is 0, we have a very, very strongly wave-dominated delta. For R is 1, we're right at the edge of wave dominance and river dominance, and if an R is greater than 1, you're river dominated. A second important part of this is that this metric that we just introduced gives us a morphologic prediction that allows us to test our hypothesis. So this brings us really away from all these descriptive studies and allows us to say something quantitatively about deltas. So I went, well, not physically to Java, but via Google Earth I went to Java, and I looked at all these different deltas, and you see that there are quite a wide variety of morphology. So some are not really very pointy, some are really pointy, and some are clearly river dominated. So we can test our metric R on all of these deltas, and if we do that, we see that, let's say we plot this ratio R we just defined by how pointy the delta is, or something we call the plan view deltaic shoreline angle, and for an R is 0, we get into a delta that barely makes any pointiness into the ocean. As we move from 0 to 1, our deltas get pointier and pointier and pointier, up to about an R is 1, where all of the deltas we find are river dominated. So this ratio here is non-dimensional, can give us some idea of delta morphology that we can then test in the field. We can also do this for a bunch of other deltas globally. For instance, the Senegal delta has a very flat coastline, and we predict that with our ratio that indeed our R is 0.04. So this is a good prediction in this case of a very strongly wave-dominated delta. For the Belize lobe of the Mississippi, we predict an R of about 7 or 8. So this is also, according to our prediction, a very river-dominated delta. And in that, I want to point out that what is very important is that this R here, we can compute without looking at the delta. And this R here is also not affected by the delta morphology, but allows us to predict something about its shape. One important case here is that you see that the Nienhuis delta in Colombia has an R of about 2. So we would predict a river-dominated shape, but if you look at this delta very closely, you see that it has very smooth coastline shape. So something interestingly happened there, and what that is this is the history of this delta. It was a river, the Nienhuis River meandered and actually broke through the beach here, and of course that's a quick way to the coast. So this delta rapidly grew here. These are all aerial photographs that started in about 1938. You see that in the first phases of growth, it was very river-dominated with a lot of mouth bars and other river-dominated features. But after 2 bifurcations, it stopped being river-dominated and attained this wave-dominated shape. So what happened here is if you have an R that would say you have more fluvial sediment than what waves can move away, if you bifurcate your river and have multiple river mouths, you split your fluvial sediment between all of these distributaries, but your potential wave power per distributary is still the same. So by bifurcating, you actually bifurcate yourself into a wave-dominated morphology. You can also do this in a simple model that we created. Let's say we just have one single channel. So this is looking at a delta from the top again. If we have one single channel, it keeps this river-dominated morphology. But if we allow this channel to split, it really effectively splits the fluvial sediment and brings it back to this wave-dominated shape. So what about tide dominance? So we first talked about this edge of the triangle here from wave to river-dominated. What about this edge of the triangle from tide to river-dominated? What makes a delta tide-dominated? Well, these are 2 pictures on the same scale of 2 completely different deltas. One is Mississippi, the other one is the Fly River in Papua New Guinea. And this has been historically characterized as a very tide-dominated delta, and this is considered a river-dominated delta. And one of the most interesting aspects of what contrasts their morphology is the channel width. You see here that this Mississippi River, the width of the channel doesn't really change as you go downstream. However, compared to this fly, it starts out being very small, and then quickly the channel width increases almost exponentially due to the tides. You can make a simple plot of that, and when you plot this channel width for different river kilometers upstream, you see that the Mississippi is pretty constant, and the fly starts out to be a lot narrower than the Mississippi, but then quickly becomes more than an order of magnitude wider than the Mississippi. And that this is because of the tides. If you have a very simple sketch here again, you see that tides go up and down. They move discharge in and out of the river mouth, and that extra discharge needs extra channel width, and that's why this river mouth is wider. So this again, similar to our wave dominance metric R, we can for tides say, well, if we have a prediction of how much wider the mouth is, this should be some signature of tide dominance. And two aspects of this predictor are going to be important. One is that we couple some external control, so things not changed by the delta itself. We couple that to a tidal flux, and we have a morphologic signature of that as well, and that is how much wider the river mouth should become. And that is will allow us to test our hypothesis. So can we quantify that? Well, let's say we have some sort of tides with a tidal amplitude that moves a tidal discharge back and forth in and out of the river mouth. And we make a very simple sketch. We can say, well, the tidal prism, or the total volume of water going back and forth, is about equal to the area of this estuary times how much water goes up and down by the tides. This volume should go in and out of the river mouth every tidal cycle. We also know from a lot of empirical studies that this tidal prism would then affect how much width or how wide the throat should be, or the river mouth should be of this particular delta. And if we didn't assume some simple sinusoidal tides, we can then relate this tidal prism to a tidal discharge. And by doing that, we now have a predictor again of how much wider this delta should be because of this tidal amplitude that moves water back and forth in and out of the river mouth. And the predictor is really very simple. It's just the width of the river mouth is equal to some upstream width set by the river plus a couple of factors, including the tidal amplitude and the length of this estuary. So it's a very simple geometric formula, and if we test that, we get an amazing fit with some of the river mouths we can simply test using Google Earth. So this is for about 70 different deltas. We measured the channel mouth width, and we also calculated this prediction that I just showed you, and we get an amazing correlation between the width we observed and the width we predicted. And from this extra widening, we know how wide this river mouth should be. We can also then calculate how much water should go in and out. And similar to our ratio R, we can then make a ratio T that says how tide dominated the delta should be. And that is just the discharge by the tides divided by the discharge of the river. And this also gives us a prediction. And what we see is that for a T less than 1, you should be river dominated. And we see indeed that the width of the channel doesn't really change as you go downstream. However, if you have a T much greater than 1, you're tide dominated, and all those tides make the river mouth a lot wider. And you see that indeed for these deltas, we find a lot of width divergence. So these rivers actually do become a lot wider going downstream. And then the other end of the spectrum, we don't have waves and we don't have tides. And in that case, the river mouth and the fluvial sediment flux by the river dominates the morphology we see. So putting it all together, we have simply created a mass balance around a simple river mouth that allows us to predict delta morphology. And that is fluvial sediment flux by the river how much of that the tides move back and forth in and out of the river mouth, or in case of strong waves, how much the waves move away from this river mouth. So now we have a general theory of what delta should look like. Can we then predict that on a global scale if we can calculate these sediment fluxes? So if we can calculate Q wave and Q tide and Q river, can we do then this analysis for every delta on the globe? Well, we have a simple wave database. This is NOAA Wave Watch, where we have a 30-year record of wave height and wave period and wave direction. That should allow us to compute this wave-dominated sediment flux for all of these river deltas. Similarly, for the tides, we have an OSU Topex tidal data set that allows us to get the tidal amplitude for every delta across the globe.
What's the time frame on that?
That is a really good question. Well, most of these are semi-diurnal tides, so it seems that like 12.5 hours is about the fluctuation you see here between high and low. And then lastly, we need to know how much sediment the river put in. And for that, we have a very empirical formula built by James Savitsky and Sagi Cohen and others, mostly at the University of Colorado in Boulder. And they have a gridded model that predicts for every delta across the globe a fluvial sediment flux. So then all we need to know is where are all these deltas whose morphology we're going to predict. So this is that same map that I showed you before, and I made this by looking at the USGS Hydroshed's global data set, which gives us drainage basins globally. And if you intersect all of these drainage basins with the coastline, you can get a prediction of where all these river mouths should be. And note that a lot of these river mouths are not typically called deltas, but they're still river mouths, and in that case, they're just very strongly wave-dominated. So putting all of this stuff together, we can then make a morphologic prediction of all deltas across the globe. So this is all these different scatter plots show you for all of these 14,000 deltas whether or not we predict them to be wave or tide or river dominated. And you can put that back in this Galloway triangle I started out with, and you see that if you color all these dots by how close they are together, you see that it's really crowded in this wave-dominated corner. However, most deltas might be wave-dominated, but if you look at the size of these individual deltas, most delta area is actually not wave-dominated, because most wave-dominated deltas are just very, very small. So I colored these dots according to the fluvial sediment flux, which should be some proxy for delta area or delta size. And you see that, for instance, the Amazon here and some of the other major deltas are mostly not wave-dominated. So that brings me to my second part. We now have a general theory of delta shape. If we know what will affect all of these deltas, can we then make a prediction of delta change? Well, from the same data set I showed you before, we can run this model and say we run it with all the dams and with all the deforestation that humans did and without. And we see that humans have greatly altered the fluvial sediment flux to the global ocean. For example, in all the Western nations, Europe and the US and also Japan, fluvial sediment flux has been greatly decreased by almost 100% for a lot of these river mouths. However, in Southeast Asia, you see a big increase in fluvial sediment flux, primarily due to deforestation that led to a big increase. So putting that stuff together, we have a prediction of how fluvial sediment flux changes. We can also project some changes in wave height from climate models. So this is a climate model where they simply computed winds 100 years from now and compared those to winds now. And they saw that wave heights in these red and yellow areas are expected to increase, but wave heights, especially in the North Atlantic and the Indian Ocean, are expected to decrease. So this will also then affect all of these deltas that I showed you before. So putting that stuff together, can we then combine those two data sets and predict something about delta change? So let's start out with the pristine distribution. So this is the delta distribution if there were no humans on the planet. And this is if we look at how all these deltas might change in the future. So all of these arrows are where a delta should be without humans and where deltas are headed towards because we've changed fluvial sediment flux and wave heights. And we assume tides are not going to vary too much on this short time scale. You see that a lot of the big deltas, a lot of the very red thick arrows are pointed down, so a lot of deltas are expected to be a lot less river dominated in the future because of humans and climate change and other natural factors. And if we can do this analysis and we can say something about very particular deltas like the Nile or the Colorado, which are expected to be reworked by waves and tides. One very important aspect of this that sets this apart from the descriptive study by Galloway is that we have a very specific prediction of the shape for all of these deltas and how they're expected to change. For example, the Nile, we have, these are supposed to be my PowerPoint sketches of deltas. The Nile goes from a very pointy delta into what we predict will be a lot less pointier delta. So there should be a lot of erosion around the river mouth because of a decrease in fluvial sediment flux. The Colorado went from a slightly tide-dominated or river-dominated delta into a very greatly river-dominated delta, which should increase the river mouth width and make it a bit more funnel-shaped tidal estuary with probably a lot more salt intrusion. But let me go back. I think I have, do you have a bit more time? Okay. This gives us a prediction of where deltas were and where deltas are going to go to, but it doesn't give us, these are two end member predictions, it doesn't give us a timeline. It doesn't say whether this should take 100 years or 10 years or 1,000 years. So how are we going to get into delta change with this extra time component? Well, we can run models and say, well, what if we look at a delta and just stop fluvial sediment supply for this particular model run? So this should be a movie soon. Seems to not this. Oh. It's thinking. Oh. Well, I can describe this movie too if I can say something about the next slide. It also doesn't want to go to the next slide. What you will see if this movie turns up is that this delta, you already see some tiny cuspate delta. In this simulation here, this delta will grow, and then we can stop fluvial sediment supply at some point in the model run. It doesn't like this. Let's see if I can go just to the next slide manually. Oh, this is also a movie. Oh. Yeah, I pressed escape a couple times, so giving me a wait. Oh, there's another one. This one is nice too. All right, so this is another one, but it gives you the same idea. So this is not the diffusive mode, but this is one where waves approach mostly at an angle, and it will start up again soon. So this delta grows, and you see instability. For years, we shut down fluvial sediment supply, and we then rework our delta. So then in this case, a giant spit developed on the downdrift side of this delta. And we can use simulations like this to get some estimate of how long it takes between these different end member points of these deltas and how much land loss is associated with that change. This is an example of such an event. So this is the Nile River, the Nile Delta, and they built a large Aswan dam in the 60s, and now the delta is being reworked. So you see that this is a Google Earth engine from the last 30 years or so, and you see that indeed there is large coastal erosion in this spit that develops on the downdrift side of the delta. So this is enormous change. This here is 5 kilometers, so the spit has degraded for more than 10 kilometers in this 30 years. I will not try to get into the other movies. But so that was a wave-dominated, this Nile Delta was a wave-dominated delta that has changed because of this Aswan Dam. And you see that the changing fluvial sediment supply of the Mississippi has also already started to see some signs of being reworked by waves. So this is a snapshot from a couple of years ago. We see that these sandy beach ridges develop off of the river mouth of the Mississippi. So we can use some of these simulations and models to get us from what should be a delta state before humans and what we expect the delta will be into the future. So my conclusion is that, well, we now have some new predictive general theory of delta shape cast in this Galloway triangle, where we know what delta shape we should expect based on where you are in terms of tides and waves. We can couple all these shape predictions to predicted changes due to land use and climate, and then combining these two data sets, we can then make a prediction of delta change for all deltas at the same time. Thank you.
We have any questions?
If you look at water depth as far as dropping off the coastline, say California, where it drops off real deep, or versus say the Gulf of Mexico, where it's shallow slope, how that would dominate
I did not look at that specifically. It shouldn't matter too much because that will greatly affect one of the things that would affect, of course, is the wave energy, and that is already, that's a boundary condition in my model. So it's incorporated in that, but just not directly. Sorry, yeah. There are two hands at the same time. You're the judge, Alex.
Did you consider the deltas in the Arctic Ocean, like the Kenzie, the Ob, and the Yenisei?
No. Well, I considered them, but I think my prediction is wrong. And that is because, of course, the sea ice and the permafrost melting will be really important in those areas, and that's not something that is in my model. But I'm actually working with people at Los Alamos to try and put Arctic deltas in my model better than what is in there now. There was a question.
My question was similar to Tom's in that I was wondering about seasonal effects such as snow melt from high mountains, even in temperate areas.
Mm-hmm.
And also growing up in South Florida, there's a lot of seasonality to the wave energy.
Yes.
And so have you looked at any deltas where you can see short-term effects due to seasonal variances?
Yes. There are a lot of deltas with a lot of short-term effects, but mostly those short-term effects affect the deltas on a very local scale. And then all of these analyses consider deltas on kilometer scales and decades or centuries. So these seasonal signals tend to kind of even out into some longer-term signal that. So yes, it's really important if you're interested in your delta next year, but perhaps not so important if you consider this delta 100 years from now. You can average those things out.
In our well-beloved Mississippi right here in New Orleans, what would you predict in the next decade? Is there anything I would see from standing on the shore?
Well, so one thing is that the wave reworking of the coastline that I think is of course the whole subsidence story is different in the Mississippi, and that's not something I can incorporate globally, so that's not in my model. But I think that might be the bigger of the two problems that we have here in the Delta. I'm working on that now with Tortornquist, but that's kind of difficult to put in a model like this. But yes, that subsidence will affect, and that will add to that barrier transgression that I showed in my last slide.
More questions?
I'm trying to think of the best way to word this, but say you, if you want to take your delta back in time, like, we can make inferences from grain size and outflow. Can you predict from just that variable what your delta might look like?
So it did like channel geometry and grain size. I think that's tough, in part because for a lot of these predictors I showed, you need analysis on a bigger scale. So for instance, you would need your channel geometry close to the shore and further upstream to see if it had diverged a lot. So if you find one channel body, you still don't really know much of the pattern of the delta as a whole. But yeah, you could make some smart guesses.
Okay, one more try. The prediction for the Mississippi is that it's going to break out at New River and go down down that way. Okay, and then that will end this arm here. It'll just become a. Okay.
Yes.
So what you're seeing, do you think that would change if this lasts, let's say, a century? Do you think that story will be modified by the changes you're predicting over the next century?
So this decrease, let's say the Belize lobe, this new Burfoot, changes, has experienced a lot of decreases in fluvial sediment supply that could be because of river dams, but it could also be because all of the sediment is now going to the Atchafalaya. So those two things for the Burfoot sake are pretty identical. And it would just, because there's no sediment supply, the equilibrium shape of this delta will be somewhere here. So it will be a strongly wave-dominated shore face in a very, very long time. Now, whether that will be 100 years or 1,000 years, that's what we need models for. But yes, that's the prediction. Does that answer your question?
I'll have to think about it.
Okay.
There's an ancillary question. While we're trying to rebuild our delta, we're also thinking that we're going to create channel cuts so that we're going to fill in the marsh and create a brand new delta. But of course, those channel cuts will also reduce the sediment supply and the velocity.
Yes.
So could you speak to that real briefly?
Well, I think that people wanted those sediment diversions because they would bring sediment closer to home instead of letting it go to waste in the Gulf of Mexico. So that's also something that is not really captured in this model very well because it's local engineering that you do to a particular delta. I think that diversions are a very good idea. And it's something that the delta would have done naturally if it wasn't for the levees we put up. So I think it's a good idea, and I think it would definitely help rebuilding land with the sediment we have.
Just curious. So if you starve a delta, river-dominated delta, and it becomes more like this wave-dominated delta. And in the meantime, we're trying to restore coastal Louisiana, and we're trying to have these big diversions. So according to what I understand in your model, that would just accelerate the retreat of the Mississippi wave-dominated system.
I'm not,
If you're taking more sediment out of the system,
yes, if you're
with the
taking more
Chapala
sediment,
and all the
yes.
sediment diversions,
yes,
then you are in essence escalating the retreat of the river itself
yes,
north.
yes. There's just a mass balance. If you put it there, then you're affecting the river.
Right.
Yes, no doubt.
So
Yeah,
how does that fit
question.
coastal
Yeah.
restoration?
Yeah, how much you love Venice, I don't know, but yes.
Not just Venice, no.
No.
I'm thinking New Orleans and Baton Rouge, actually.
Well, but most of the sediment diversions are still seaward of New Orleans. So they're Myrtle Grove and then in that area. So I think they're more useful for New Orleans than further out into the Gulf. So I think, yeah, those diversions are